Hey, how's it going, everyone? I hope you're having a fantastic day. So, basically, over the weekend, I tried to fine tune a model on our community book called the Circumfusion, and the results were quite surprising. So, I cannot wait to show you that in this video. All right, before we dive into the code, I just want to explain how models understand. It's all about context. Models have been pre trained, especially base models, so that they can understand general language and a bit of reasoning. Basically, a model that can produce text one token at a time. And like I said, it has general knowledge because it's been trained on so much knowledge from the web and many different sources. But it's not an expert. For example, if you had to ask it a question about Picasso, it might tell you that Picasso is a very famous artist, but it might not know the inner details of Picasso's life. So, if we want to make it an expert, we need to give the model more context, and there are various ways we can do so by using things like prompting, fine tuning, parameter efficient fine tuning with LoRa, RAG. There's also MCP tools that can be used, and lots more. So, in this quick section, I'm just going to show you the different ways where we can add context to a model to make it an expert in the field or become something totally different. It's very exciting. So, the most basic way of adding context to a model is what we do when we chat to it. We give it text, we give it a prompt. But what if we took an article of Picasso and added it with our prompt and then send it into the model? Now we've added context and the model has something to work with. And now with this added context, it can give you a better output on who Picasso was. Another way to make a model an expert in a topic is by actually fine tuning it. And this is where we take the base model and we configure and update all of its parameters. Basically, taking tons and tons of data about Picasso, an artist, and his career, maybe all of his exhibitions he had, all the artworks that he did, and we train this model on who Picasso really was. And we can add other and various artists in there too. The model's weights will then be updated, and when it's prompted without giving it any extra context, the model can roughly figure out who Picasso was and give you that response, provided that it was trained on enough data. Now, to fine tune a model does take a lot of resources because you need to update all the model's weights. So, there's a better alternative to this if you want to do the same thing but on smaller resources, and it's very efficient. And this can be done with parameter efficient fine tuning using LoRa, low rank adaptation. Basically, doing the same as fine tuning, but only fine tuning and updating a small portion of the model's weights. This is very efficient, fast, and also gives you very good results as if you were to fine tune the entire model. And although there's benefits in fully fine tuning a model and only updating partial weights in a model, it comes down to your use case and also your resources. If we want to do this, which we'll be doing today, then I need to go and use LoRa to fine tune my model so that I can do it on my home computer. We have to remember that each one of these mechanisms of adding context, one might be better than the other one for different use cases in different scenarios. For example, today I am going to fine tune a model on the book, but in reality, there is a better way of giving it context, maybe with RAG, which we'll talk about next. However, I do want to try fine tuning it because I'm curious and I want to learn how all this works. Speaking about RAG, this is just another way of adding context to a model. It stands for Retrieval Augmented Generation, and it's basically the same as just prompting with text. Like we did before, where we added Picasso's article to the prompt, this is exactly what RAG kind of does. But instead, RAG depends on a vector database, a database that's been trained on your data or given your data to embed. And then when you give the model your text, it first looks up in this database anything relevant to what you are asking, adds it to the context, and then sends it through the model. It's simply another way of bulking up your prompt with more context. And now we cannot forget about MCP, which stands for Model Context Protocol and basically allows LLMs to use certain tools like APIs or update a booking when you're going on holiday. And essentially, how this all works, which it definitely deserves its own video, but basically, you've got these MCP servers which are set up by companies who exposes APIs to their tech. And then basically the client or host can let a model know what tools are available. So as the model thinks and it needs some data, it can actually reach out, call one of these tools, and retrieve data on the fly. So it's a way for a model to get real-time context as it's generating and going back and getting more data, and also extending functionality to an LLM. However, today, like I said, we're going to focus on parameter efficient fine tuning with LoRa, and let's dive into it and let me show you kind of the process I took when I decided to train the model on a book. All right, so the first thing we need if you want to fine tune a model is an actual base model. Now, you can find a base model by going to Hugging Face. They've got a whole model section, and I like going to the license section, choosing an Apache or MIT license model. This makes me feel good that I can use it and give attribution to the creators, but I can freely use it. When it comes to choosing your base model that you want to start fine tuning, it's important to consider a few things. Like, for example, what do you want the output to be? Do you want it to be some kind of chatbot? Do you want it to be a LLM that's good at following instructions, or an LLM that's very good at coding? Well, you can kind of dig around and find the model that will suit your use case. I like going to the trending section to see what people like to download and try and fine tune. Also, some of these have been fine tuned on top of other models. Another thing to consider is the parameter size. For example, on my M1 Mac, I feel comfortable training models that's around about 1 billion to 3 billion parameter size. I can definitely not train 8 billion parameter size models, at least if I do not want my machine to blow up while I'm recording with OBS. Do a bit of research on the hardware you have and what models people have fine tuned. Today, I'm going to focus by searching for Tiny Llama, this Tiny Llama 1 billion chat model. Now you can also see that it has a ton of downloads, and this model itself was fine tuned on top of another model using this data set. And that means you can actually go ahead and have a look at the data set that this model was trained on. How cool is that? This is also on Hugging Face. And if you go to the dataset section, there are tons of data sets also with licenses that are free that you can use to train on. It's really cool. For today, I don't need that because I already have a data set, which is the community book, which I'm just going to pre-process. Now, if we move on from this, they also show you a bit on how to run the model. So now that we have the model selected, we can now move over to the code, and I'll show you the script that I've created to fine tune this model. I think it's also worth mentioning that a way to fine tune models these days, there are also various libraries that makes it now more efficient so that you can train larger models on low resources like Onslaught. So you can go and check that out. There are many tutorials on this. I have not looked at this yet, and maybe I will in a future video, but that's just a good thing to mention. For now, we are just going to do it with the Hugging Face library and LoRa and parameter efficient fine tuning to produce a model that we can use. All right, so I'm going to go over the code. I'm going to explain some of the snippets, but this is not a step-by-step tutorial because it's going to take quite a long time, and I want to become way more confident with fine tuning before I actually make a step-by-step tutorial. But you'll see all the code that was used. Now, the first thing is our data set. So we have this book, The Circumfusion. This book was created in collaboration with hundreds of community members from the Sketchy Lab community, and I think it's a perfect piece to use when it comes to fine tuning to see if we can actually ask some questions about the book later on. Now, I have all the text of the book in this one text file. Now, having the text is great, but we really need to start processing this data set so that we can actually feed it into the chat LLM so that we can ask it questions and it gives us answers back about the book. So what I then did was I went to ChatGPT and I asked it to convert the chapters into questions and answers. And what it gave me was questions in a JSON-L format and answers. So JSON-L is basically this line-by-line object file where we've got an object with a question and then an answer field. And you can see there are many of them. Now, great, we've got a data set, at least the starting point of a data set. We still need to convert this into a template where there are roles associated to a system prompt, a user, and the assistant, and then taking the template and formatting our dataset so it's ready for the LLM to be trained on. Now let's take a look at the training script. At the top for the imports, we're going to use the auto tokenizer, the auto model for causal LM, the trainer training arguments from the transformers library from Hugging Face, and then from the PEFT library, we're going to import LoRa config and then get PEFT model if we want to save it. Then dataset from dataset library, torch, and JSON. Next, we have some configuration, the model name, which is the Tiny Llama, the 1 billion chat model that we just saw on Hugging Face. We've got a dataset path, which is the path to our JSON-L file. Then an output directory, which is where the model will be saved. And I actually ran the script. I'll show you the logs just now, but it's already there, saved and ready for us to use. And then we also define the system message. In this case, I'm saying you are a helpful assistant that answers questions about the book Circumfusion. Great. So next, what we have is a function over here, which basically is going to format our data set that we have, our JSON-L file. Is going to format that and push it into what the model is going to expect. A format that looks like this with the role system prompt, which we have up here. We also then going to take each question and have it as the user. And then also for the answer, we'll assign that to the assistant. And this will nicely format our data set. So we'll create a variable and store it here in the QA data. And then what we're doing is we're splitting this data set to have 90% of it be the training data set and 10% of it be the evaluation data set. Now, this part confuses me a little bit, and I'm going to be honest. I'm going to use 10% of it to evaluate how our model performs. And the hopes is that the model has trained enough on this data to know the way that the book is written to be able to generate answers in that style. And that's essentially what this evaluation data set, I believe, is needed for, to kind of test if the model can produce text close enough to what it was trained on here. Why it confuses me is because it is kind of like strange, right? The model will have never seen this data, and yet we expect it to evaluate itself against it. Maybe this part I'm doing a bit wrong, but let me know in the comments if I am. I would love to learn more. However, this is what we're going to use. 90% to train on, and then 10% to evaluate on. The next step is we're going to define the tokenizer from the auto tokenizer and from pre-trained our model. We're also then going to set the padding token to pad if there isn't any padding token. And then we load the base model using the auto model for causal LM from pre-trained model. And we're specifying that this is going to be float 32, basically because I'm doing it on my CPU. And then I'm going to resize the token embeddings, making the model aware of the new pad token if it wasn't before. All right, so now it's time to specify the LoRa config. So basically we instantiate the LoRa config and we pass it the task type, basically saying what LLM task are we performing. Then also we specify the rank. The higher this number, the slower your training, because the more parameters will be updated and changed. So essentially we're just putting it at 16, which should be fine for my CPU. Then we get the LoRa alpha, which essentially measures the control of these adapters and how much effect it will have on the model. And then we have the dropout. As far as I understand it, this is preventing it from overfitting, meaning that to train it so well that it kind of gives us very deterministic responses. So we do not want to overfit the model. And then we specify the target modules, which is essentially the layers that we want to have LoRa configure and adapt. Basically, these are the attention layers. And these are the ones that kind of matters the most, right? And so these are the target layers that we want to update. And now we can apply the LoRa config to the base model by using getPathModel and storing that in a variable. All right, so now it's time for us to define the tokenized function, which we'll take in the examples. What we want to get out of this tokenized function is the tokenized inputs, the attention masks, the labels. Remember the input IDs and the labels, they need to be the same because the labels are kind of the checkpoint, the validation tokens because they are the ones that is shifted either to the left or the right for the model to predict the next token. And then the attention mask is there to tell the model what is relevant to train on. So then we're going to loop over the examples. We're basically going to format the text and then pass it through the tokenizer, passing in that text. And then we're going to put the max length of context to about 512, which is a good context length. And then lastly, we just go and append the input IDs to this tokenized input IDs, and then basically attention mask and so forth and so on. So we can get this returned. All right, so now that we have our tokenized function, let's turn the text into tokens. And basically we can do this for both our data sets. So we've got the training data set and we've got the eval data set, right? The evaluation data set. And because they're data sets, they've got this map function, and the map function can take in a function that we want to run on the data. We can also then set batching to true. It will make it faster. We can remove any of the columns. So we have our tokenized training set, and then we also have got the tokenized evaluation set. All right, so now before we can continue, we need to kind of organize our data. We need to organize the data and also pad the data so that they all have the same sequence length. Because remember, our answers and so forth, they're not the same length. They are varying lengths. So we need to add padding to it as well. So to not bore you with the details, because all it's doing is basically extracting the tokenized features essentially from the sequences. And then it's going to look at if they have varying lengths. And if they do, we're going to pad it. So let me show you in a visual way. So let's imagine that basically the data that we are analyzing is our batches, right? So let's say we have got a batch size of 2 here. We can see that the first sequence has 4 and the next sequence has 6 of length. So basically we want them all to be 6. We want them to be the same sequence length. And so what this means is that it will eventually come out looking like this. Basically what this is we have now padded these sequences to be the same length. So we've added here 0, 0 to accommodate for the length to be 6. And then here in the intention mask, what's interesting is that you'll see we've got 1, 1, 1, 1, 1 and 0, 0. And there we've got 1, 1, 1, 1, 1. It's saying basically pay attention to the first 4 characters because that's what matters in this first sequence. All right, cool. And so that is it for padding and making sure that our sequence lengths are all the same. Next, it's time for us to define the training arguments that we're going to pass to our trainer. For the arguments, we're going to instantiate training arguments. We're going to pass it the output directory where we want the model to be stored. We're going to also define the number of training epochs. So basically, an epoch is how many times the model is going to have to run through the data. Then we have the batch size. We just have 1 here. I feel like it's okay for this chat format. And then we have the learning rate. Now you can play around with this. The higher this number, the faster your model is going to train. And basically, if it's too high, it can do overfitting. So if it's too low, then it does underfitting. It doesn't really learn something. So you have to kind of play around with the learning rate. And this is also what makes fine-tuning fun, right? There's so many parameters and there's a lot more that you can kind of fine-tune and get the feel for how your model is performing. And then we've got the eval strategy. We've got how many steps, every steps, 10 steps we wanted to evaluate, how many steps should we save a checkpoint, and then also on how many steps do we want to log so we can actually see output and like loss and things like that. And then report to none, and these I just left as it is, as I saw from some documentation. Basically, now we get the trainer. We're going to pass in the model that we set. Remember the parameter efficient with LoRa and the base model. Then we also have the training arguments we specified. We've got our tokenized training data, our tokenized evaluation data, the data collator, and then also the tokenizer. Now with this, we're ready. We've got our trainer ready and we're ready to train. So all that's left to do is we create a variable for the results and we can go ahead and say trainer.train. Lastly, what we can do is we can actually save the LoRa adapters, which we can then use on any other tiny llama model later on. Basically, this is a very small, small files. So that's pretty cool. But then we can also go ahead and merge the LoRa adapters into the base model so that we have a final model that we can run inference on. Now I ran this and I'm going to show you now the screenshots of me running it because I can't run it with OBS running. This will definitely bug out the recording. So let's go and see what happens when I run this. Now, when I was running it, I also had a bunch of print statements added so that I can actually see what's happening. So the model was loaded and here you can see that we have 1079 Q&A questions for our data set, right? From that JSON file that we had. By splitting it to that 90-10%, we ended up with a lot of questions and answers that we're going to train on, and also 108 validation questions and answers. Okay, so here we created the data set. And then we loaded the tiny llama model. Now it's pretty cool. You can see the vocabulary size, right? How many of these word subword tokens it has in the model, which is 32,000. And then also you can see all the parameters. So we can indeed see that this is a 1.1 billion parameter model. I have to say, the more I'm learning about LLMs and how the models function and kind of learning about their inner workings, and then physically seeing it when you print it out and you're working with them in code, it kind of puts it all together nicely. Now, let's carry on. So basically then the LoRa configuration was configured. Remember the rank we set to 16. And this means that the trainable parameters for us is going to be 4.5 million weights out of the 1.1 billion, meaning that the trainable percentage that we're going to train this model is merely 1.4% of the model. And that's why it's so efficient to train with LoRa. Now, as the model ran, you can see that it started doing these printouts. Now, in each printout, we get the loss. And remember, the loss is calculated when it's worked out kind of against its label, how correct it was. And then it tries and corrects itself and updates those parameters. We also see here at the end, we see the epoch and kind of basically the percentage of data it's running through. Remember, we have one epoch set. So once that's done, then it's complete with training. But something to note here is that you can see how the loss kept on going a bit lower, lower, and lower. And here's another snippet as it was approaching the end, and you can still see how the loss was going still lower, kind of rounding about here. Now, in between the loss, we also have these evaluation steps. And so you can also see as it's being evaluated that this is also improving. Here it's 1.5. Here at the bottom it's 1.49. And here it's 1.498 and so on and so on. Now, sometimes it climbs up a bit. I guess that's because, we are training or testing it against data that it's never seen and we're expecting it to generate something close to it. So I guess that is kind of expected. Now, at the end, it ended up with a training loss of 1.41 and a perplexity of 4.10. Now, the lower the perplexity and kind of the lower the loss, the better, right? Unfortunately, I'm not an expert on training models or fine tuning them yet, so I'm not sure if these numbers are really good, kind of good, or really bad. From what I read, this is okay, but we're going to test out the model because the proof is always in the pudding, right? So we're going to test them out right now and see what it gives us back. All right, so in the terminal, we're going to run some inference. Now, the models were saved here. As you can see, these were the checkpoints for the LoRa that was saved. And then we also have basically the merged model that we're going to run. Now I've got the pipeline up open here that I'm going to run first. And just to show you what this is, I'm trying to run the base model, so the tiny llama, without any fine tuning. And I'm going to ask who is Ethan. Now, Ethan in our story, right? If we just search for Ethan, is a character and he pops up quite a lot in the book as well. So we kind of expect if we successfully fine tune our model that it should know. But firstly, we're going to expect that the base model, the tiny llama model, should not know who Ethan really is. Maybe it picks up a Ethan, but it shouldn't pick up the Ethan in the book. So let's run it. We're going to ask the generator to generate this question through the base model. And let's see what it gives us back. All right, so essentially I asked who is Ethan, and the model told us that Ethan is a young boy who loves playing video games and hang out with his friends. That doesn't sound like the Ethan in the book. Okay, the Ethan in the book, they on this whole sci-fi kind of journey, and basically, I want to see things like scientists and so forth. So now, what I'm going to do is I'm going to run the custom LLM that we have. So I'm going to go here. This should already be configured to run on this merged model. And here I'm just telling it that it's going to be a helpful assistant. And it works a bit differently with the inference here because I'm just going to kind of have it be like the chatbot where I can actually ask it for a question back. All right. And then here, but I want the exact same question. Who is Ethan? Okay. So let's go ahead and run this. So that's going to be the pipeline QA model and then dry run. All right, so we can see we asked the model who is Ethan, and it said Ethan is a researcher working for the Sketchy Labs. Now, it also says he was involved in the fake ID experiment that led to Alice's transformation. Now, sometimes the model's not going to get everything right in this book, but the fact that it knew what the Sketchy Labs is and it knows that Ethan is a researcher of some sort, right? It kind of is starting to pick up on the characters, kind of linkages to characters. The fact that it linked Alice to Ethan. All right, cool. Let's try this again and let's say what other characters are important in the story and see if it can give us some character names. Now, I have to say, I think by doing this and fine tuning a larger model is going to be or give a lot better responses. It is giving okay responses, and I can tweak the way I'm fine tuning so that basically maybe it improves how the parameters are set. Maybe I must tweak the learning speed and so forth. But I must say, I can see slithers of theming coming through from these answers. For example, here it's saying several other characters, nurses, researchers, detectives are introduced through flashbacks and providing insight into conspiracies and the underlying scientific motivations. Like that is all true. There is, detectives and conspiracies and scientific motivations. There's all that in the book, but yet now it didn't give us back the characters, and that might just be maybe a lack of the reasoning of this model and not necessarily the fine tuning. So that's why I'm saying maybe a larger model and playing around more with the fine tuning as well. However, let's ask it, can you name a few as well? So I'm going to run this and we'll see what the output is. But all in all, I had so much fun doing this. I cannot wait to start really playing around with it, trying a few different things, trying to, like I said, adapt the learning speed, trying to optimize my data set. I don't know how I'm going to increase the data set. But another thing to note is, like I said in the beginning of this video, fine tuning with LoRa is not the only option and sometimes not the best. I also think that if I use a larger model and just use RAG or just add this into the context, if you have a large enough context, whatever the case might be, we might get better responses. So it's all about deciding what the scenario is. But for this experiment, we just kind of trying the fine tuning mechanism. So I'm going to run it again as I see that it did give us an answer, which is Jaron, Sam, and Gilly. And if we go and search in the book, we can certainly see Jaron here. I think there's a Sammy. Oh, there's Sam's, right? So that is good. We can also see now it gave us more character names. And here we go. It gave us Ethan. And remember, this has no memory, so it cannot base this off previous things that I told it here in the chat. Also, Alice is there. And it also speaks about the turning point from research to the real world action. Okay, there's a lot of theming throughout this all. Now, I must say, that I'm quite chuffed with the fact that we got to fine tune an LLM. And although it's not perfect, although it's not the best question and answer bot for the Circumfusion book, I think with a bit of more fine tuning and a bigger model, maybe I'll try that on Google Colab, is it's certainly going to be something really cool to have. I'll also play around with the other mechanisms I've mentioned, and I will report back and we'll see how it goes. For now, I'm continuing on my journey, learning about LLMs and all the wonderful things we can do with them. I hope that you enjoyed this video today. If you did, let me know in the comments and give this video a thumbs up if you did enjoy it and you want to see more content like this. Apart from that, let me know what you're working on. If you also into AI and kind of learning how LLMs work, I'm keen to find out what everyone's working on. So, cheers for now, and I'll see you in the next video.